Welcome back to MathXplore Infinity. Today we embark on an exciting journey into the realm of cutting-edge mathematics, specifically exploring two remarkable theorems in functional analysis, notably the Stampacchia theorem and its renowned corollary, the Lax-Milgram theorem. Lax-Milgram is a household name in the world of mathematics, right? Commonly invoked when dealing with partial differential equations, but it is often seen as a direct consequence of the powerful Stampacchia theorem. Now, let's try to bridge the gap between these abstract theorems and the real world. Imagine you are an architect, right? You are tasked with designing a bridge with specific load-bearing requirements and constraints. You need to optimize the bridge shape, right, while ensuring that it can withstand the expected load. So this complex engineering challenge involves both optimization and mathematical modeling. Optimization in the sense that you want to minimize the material used for the bridge, right, while meeting safety and stability requirements. And mathematical modeling, because you need to represent the bridge shape mathematically and describe how it responds to different loads. So Stampacchia's theorem and its corollary, the Lax-Milgram, come into play in the following scenario. Stampacchia's theorem actually assures you that under certain conditions, you can always find optimal shape for the bridge, right? That minimizes material usage while satisfying structural constraints. This is like discovering the perfect design for the bridge, right? Even when you don't have all the exact mathematical details. The Lax-Milgram theorem, on the other hand, which is a specific result that stems from Stampacchia's theorem, ensures that when you solve the mathematical equations, the PDEs, right, describing the bridge behavior under various loads, you will not only find a solution, but also guarantee its uniqueness and stability at times. So in other words, Lax-Milgram theorems guarantees that your bridge will perform as intended, right? Even when dealing with complex equations and loads. So to cut the long story short, Stampacchia's theorem and the Lax-Milgram theorem provide the mathematical foundation to tackle optimization and linear equations problem, right, respectively. They assure engineers, scientists, and mathematicians that solutions exist and are unique under specific conditions, making it possible to design and analyze a wide range of real-world systems and structures. So these theorems are, I would say, the safety net, right, that make complex mathematical problems solvable and engineering designs reliable. Now, if you are as inspired or captivated as I am by the elegance and the power of mathematics in solving real world challenges, subscribing is more than just an option, right? It is the key to unlocking a treasure trove of knowledge. So it would be, I feel like it would be a travesty, right, to miss out. So I strongly invite you to join our MathXplore Infinity community, and together we will embark on an endless journey into the boundless world of mathematics. So let me, well, but if you feel not convinced, right, not convinced enough, let me put it this way. Think of each video as a new bridge to cross, right? A new horizon to explore. And not subscribing would be like stopping at the edge, right? Missing out on the breathtaking view. So seize this golden opportunity, hit that subscribe button now, and let's dive deeper into the mesmerizing wonders of mathematics together. I mean, don't don't merely watch the from the sidelines, right? Be an active participant in this mathematical revolution and elevate your mathematical skills to unprecedented heights. So, before stating any of the theorem that we are going to talk about, let's have some, a definition. So, definition. So, by linear form, bilinear form that we call A, right, defined on H, right, is said to be, so the first definition is continuity. So the bilinear form A is said to be continuous, right, if there exists a constant. I mean, this is the usual definition we know. If there exists, and of course, a positive constant, right? Constant C, positive, such that put it in color, the absolute value of A of U, comma V, right? First equal than C times the norm of U times the norm of V, right? And this of course should hold for every U and V in H. So the second definition is about cohesivity. So a bilinear form is said to be cohesive if there exists a constant, if there is a constant, we call it alpha this time, positive, right, such that A of V comma V, right, is greater or equal than alpha times the norm of V squared. And this is of course, for every V in H. Okay, good. So now we know what continuity and cohesivity mean for a bilinear form. Okay, so we are ready to state our first theorem, right? And this would be Theorem 5.6, and this is this Stampacchia theorem. This is Stampacchia. Let me fit well, but it looks a bit ugly. Let me just try it a bit. Put on some modifications. Okay, good. Good. So this is the theorem of Stampacchia. Now, what does it state? So assume that you have a bilinear form, this Cartesian product. So assume that A is a continuous. Let me just put it in color. It's a continuous cohesive and bilinear form on H. Right, so let me just highlight. I mean, those are really important actually. We change the color. Continuity, cohesivity, and bilinearity. Very important. So assume you have a continuous, cohesive, and bilinear form on H. So let's call it K, right? Be a non-empty closed and convex subset of H. right? So again, let me just highlight. Unit closeness set to be non-empty and convex. Okay, so then given phi, given any linear bounded operator on H, right? Given phi in the Joule space, there exists a unique, put it in color, there exists a unique element that we call U, right? I put it in quotation mark, a unique element U in K, right? In the closed non-empty convex subset of H, such that we call this relation 10, so maybe I use this color, such that 10 hold. This is A of U comma V minus U, right, is greater or equal than the Joule pairing of phi with V minus U. Right? Again, as I said, this is the Joule pairing, right? So don't confuse it with the scalar product. This is just another way of saying phi of V minus U. So there is a unique U such that relation 10 hold, of course, for every V. So to be consistent, for every V in K. Moreover, if our bilinear form is symmetric, so if moreover, if A, right, is symmetric, then we can even characterize U, right? Then then U is characterized by the following property that we call 11. Call it 11. So this property says that U is in K. This is what we know already, and 1 over 2 of A of U comma U, right, minus this dual pairing of phi and U. This is this is, there's no place, but this is should be equal. It should be equal to the mean over the V in K, right, of 1 over 2 of A of V comma V minus this dual pairing, no place. So if A is symmetric, we can even further characterize U by 11, right? So just so you not to get confused, this means that U is exactly this is probably an abuse of notation, but you should understand that this is a singleton, right? So this is just an element minus phi comma V. So this is the arc mean of this over the V in K. So the proof of this theorem actually relies on the following classical result, right? So that I will recall. So this will be theorem 4.7. We'll come back to the proof, so don't worry. So the proof relies on this theorem. This is the Banach fixed point theorem. Banach fixed point this hyphen between fixed and point. Yeah. Banach fixed point theorem, also known as the contraction mapping principle. Oops. Okay, so let me recall very quickly the Banach fixed point theorem. So let X be a non-empty complete metric space. Right? So let me just highlight key properties of X should be non-empty and complete metric space. And let's call it S, right? Be defined from X to X, right? Be a strict contraction. Strict contraction is just similar to Lipschitz continuity, right? Just that the Lipschitz constant should be between 0 and 1, strictly less than 1. So let X be a strict contraction, right? So this means, just write down what it means, that the distance of S of V1, S of V2, right, is less or equal than K times the distance of V1, V2. Of course, this is for every V1, V2 in the space X, right? If the Lipschitz constant, as I said, between 0 and 1. Okay, so under these conditions, then S has a unique fixed point, right? That will be called U, right? Which is S of U again, right? Because it's actually a fixed point. U is mapped onto itself. So, an example of some fixed point you can consider, for instance, this map, right? This parabola, and 0 and 1, for instance, would be fixed point for this map, right? Defined from R into R. Okay, so let's have, this is not the complete proof, this is just the proof idea, right? How you can prove the Banach fixed point theorem. Okay, so first thing is that you move from the fact that your space is non-empty. So since X is non-empty, right, choose any element, say V0 in X, right, and define and construct or define the sequence Vn, right, where defined by Vn plus 1 is S of Vn, right, for every n. So Vn is defined recursively by this relation. So your first step, right, first step of the proof would be to show that Vn is a Cauchy sequence. Right? And because once you show that it's a Cauchy sequence, and because we are in a complete metric space, and consequently, Vn converges to certain v in H, right? I mean, or in X, because we use X in the H1. Okay, so the second step would be to show that V is a fixed point, right? But this is relatively easy, I would say. So to show that it's a fixed point, so you can, it's enough for you to show that the distance of V to S of V is equal to 0, right? And then you can conclude using the separability of the distance. And this can be achieved, this can be achieved via the triangle inequality. Right, so you just include Vn, and then it's not something difficult. You can, I'm pretty sure you can do it. So, and in the final step, right, final step would be to show the uniqueness of V. So this would be the idea of the proof, and with that you are done. Okay, so now let's come back to the proof of the Stampacchia theorem. So proof of theorem 5.6. So the idea of the proof is that we are going to break the initial problem into another problem which is easier to solve, right? And then we will solve it using, of course, the Banach-Fixed-Point theorem. So we are given, so let phi be a linear bounded operator on H, right? So it follows from the Rees-Fréchet representation theorem like this is actually theorem, I think it was theorem 5.5. I actually invite you to watch the video on the dual of a Hilbert space, right? So I will put the link at the upper right corner. So let phi be a linear bounded operator. So by the Rees-Fréchet representation theorem, right, there exists a unique, we call it F, right, in H, such that this dual pairing is again the scalar product of F and V, and this is of course for every V in H, right? Okay, so again, this is a scalar product, right? So don't get lost or confused, right? And the other one is the dual pairing. Now, on the other hand, for fixed U in H, right, the map A of U dot is the placeholder. This map is defined from H to R, right? Which take the V and maps to A of U comma V. So this map, because A is a bilinear form, this is a continuous. Linear functional on H, right? So what we are basically saying is that A of u comma dot, right, is an element of the group space, right? Now using once more, the refreshed representation, oops, I'm writing so big. So this is using once more the refreshed representation theorem, right? There exists, I mean there is some unique element in H, right, that will be denoted by AU, right, such that, again, I mean the story is the same, A of u comma v, right, is equal to this scalar product of AU, of AU comma v, right, and this is of course for every v in H, right. Now A is obviously, I mean, A is clearly a linear operator, just even bounded, but let's go slowly. It's clearly a linear operator from H into H, right? Because well, if you have I mean u1 and u2 in H and alpha is scalar, right? A of u1 plus alpha u2, right? Sorry, comma v. So this is exactly equal by the representation theorem by A of u1 plus alpha u2 comma v, this scalar product, right? But maybe I use another color. But A is a bilinear form, so this is exactly again A of u1 comma v plus alpha A of u2 comma v, which is again equals to AU1 in this scalar product, right, plus alpha of the scalar product of AU2 comma v. So you see that this quantity here is exactly, I mean, should be equal to this. So you have linearity. Of course, this is for every v in H. So A is clearly a linear operator from H into H, right, and satisfy we call it relation 12, satisfy the norm of AU, right, is less or equal than C times the norm of U for every U in H, right? Well, I mean, this is again easy to see this, indeed. I mean, this is kind of a short proof. Indeed, we have that this is by continuity of our bilinear form. This is less or equal than C times norm of U times norm of V. Of course, for every U and V in H, right? So this means to take the supremum, right? Supremum of the absolute value of A of U comma V, right, over now the V in H, so that norm of V is less or equal than 1. So this is actually less or equal than C times norm of U. But observe that this is nothing else than the operator norm of A of u comma dot, right, in the dual space. But this operator norm, by the resubstantiation theorem, right, we saw that we also have an isometry, so that this norm, this operator norm, coincide with the norm of AU, and the norm of the representant. So this is therefore less or equal than the norm of U. Again, I said this equality here, use a different color. This is the race freshet in one of the consequences. Okay, so A also satisfies relation 13, which is in the scalar product of A of u comma u is greater or equal than alpha times the norm of u squared, and of course for every u in H, right? But this is kind of straightforward to see because this is again A of u comma u, right? And then we know that A is cohesive, right? So this obviously holds. So problem 10, right? What do you want to show? So problem 10, maybe I recall problem 10, what we want to show first. That is, problem 10 is about finding u in the subspace, the subset K, right? Such that A of u comma v minus u, right, is greater or equal than phi of, let me just write it with the dual pairing. So it's greater or equal than phi of v minus u, right, for every v in K. So problem 10 can be, rewritten or amounts to finding u in K, right, such that hold, such that scalar product of A of u and v minus u, right, is greater or equal than scalar product of f comma v minus u, right? So those problems are equivalent for every v in K. Okay, as I told you at the beginning, we are breaking the original problem into a simpler problem, right, which is easier to solve. Now, let rho be positive constant, right? The constant, this constant is to be determined. Just keep that in mind. So let me determine later. I'll tell you why. So let rho be a positive constant. Observe that, if you multiply relation 14 by rho, the inequality doesn't change. And then you can just basically pull the left hand side to the right hand side and do some basic arithmetics using linearity of the operator A. So observe that 14, just writing like this, 14 is equivalent. We are again breaking 14 into another problem. 14 is equivalent to, we call it 15 now. It's equivalent to the scalar product of rho f, right, minus rho a u, right? I'll do something here now. Plus u minus u, comma v minus u is less or equal than 0. Right? It is something very stupid, but very crucial here. I mean, observe that this is 0, right? So problem 14 amounts to finding u such that this relation holds for every v in K, right? But if you see, I mean, if you look at relation 15, you see that this is just the characterization of the projection onto the subset K. So this is problem 15 amounts to finding u, right? Such that u is just the orthogonal projection, or the projection onto K, the convex closed non-empty subset K of rho of f minus rho a u plus u, right? So again, so we just write it here. We need to find u, right, in K such that, I mean, this relation holds. Good. So you see what we are, I mean, simplifying problems over and over again, right, until we get the perfect form. I think here we are basically done. Now for every v in K, right, put S of v, right, to be the projection onto K, right, of rho f minus rho av, right, plus v, right? Now we claim that, this is our first claim, so we claim that if rho, which is positive, right, is chosen properly, then S is a strict contraction, right? And then if S is a strict contraction, we are done, right? Because you will have u equal to, I mean, you will have u equal to this exactly, and then you can do kind of reverse engineering and find out that u solve for 10, and 14 is, I mean, it's equivalent to 10, and we are done. Okay, so if rho is chosen properly, right, then S is a strict contraction. So let's see how this is possible. So indeed, since projection, since pk does not increase distance, I mean, we saw that projection is non-expansive, does not increase distance, right? That is another way of saying that pk is non-expansive. By proposition, I think this was actually non-expansivity was, says this, that pk of say of u minus, probably I use different, of u1 minus pk of u2, right? This is also equal than the norm of u1 minus u2. So since pk does not increase distance, right, this was actually a proposition, we put it in bracket for your reference. This was proposition 5.3, right? So check out the lecture on Hilbert spaces, some elementary properties. I'll put the link if possible. Yeah. So since pk does not increase distance, we have that the norm of S v1 minus S v2, right, is also equal than the norm of v1 minus v2 minus rho of A V1 minus A V2. Right? I mean, you just need to remember how S is defined. Right? So you just need to write things down, and then so there's nothing special here. So on this, we should square both sides of the inequality. We get that the norm of SV1 minus SV2 squared is less or equal than, and this is now about expanding the right hand side. This is less or equal than the norm of V1 minus V2 squared minus 2 times rho of the scalar product of A V1 minus A V2, but A is linear, so I can even write A V1 minus V2, right, comma V1 minus V2. Okay, this scalar product plus rho squared of the norm of A V1 minus A V2 squared. Now I will jump a step and just write that this is less or equal than the norm of V1 minus V2 squared times 1 minus 2 times rho times alpha plus rho squared c squared. Well, here I apply the coercivity of A, right? Coercivity of A was applied, right, in the sense that you saw that A of u comma u, right, is greater or equal than alpha norm of u squared, right? So coercivity occurs here, right? And now continuity of was also applied, right? Continuity of the, of the operator A. This is the norm of V1 minus V2 is also equal than C times the norm of V1 minus V2. Okay, so choosing rho positive, right, in such a way that, let's call it k squared, right, that we define to be 1 minus just 2 rho alpha plus rho squared c squared. So if we choose this k squared to be strictly less than 1, right, so we can basically simplify the ones here, right? So this means you should choose rho to be strictly greater than 0 and strictly less than 2 alpha over c squared, right? You can make the computation. We find that S is a strict contraction, right? I mean, just take the square root of the relation above. It's a strict contraction, and by the Banach fixed point theorem, we write it here, S has, maybe not, S has a unique fixed point. Right? What we are saying is that there is a unique u in K, right, such that u equal to SU, which was defined to be projection onto K of rho F minus rho AU plus U. So this means that 10 holds, right? So that problem 14, 15, and 10 were equivalent. So 10 holds. Now we want to show that, let me just write it. So we are all on the same line. So now we want to show that if our bilinear form is symmetric, right, then this was 11, u is in k, right, and u is mean the arc mean of the following quantity, 1 over 2 a of v comma v minus, you just write phi of v since there's no place anymore. So this was I think this was 11. Yep, looks ugly. Okay, so this is what we want to show now. Now assume now that A is also symmetric, right? Then A, right, defines a new scalar product on H. Right, and the corresponding norm that we call norm mu, right, is defined, this is just the square root of the scalar product, right, to the power 1 over 2. So the corresponding norm mu is equivalent to the original norm on H. Right, because you have that alpha times the norm of u squared is less or equal than a of u comma u. This is by coercivity, right? And now by continuity, you have that this is less or equal than c times norm of u squared, right? So this means if you take the square root, you get that square root of alpha times norm of u is less or equal than norm u of u, right? Because the norm u was defined to be the square root of a of u comma u, which is also equal to square root of c times norm of u, and this is exactly the definition of two norms being equivalent. So it follows that, because, so let me just write it first. So it follows that H endowed with this new scalar product, right, is also a Hilbert space, right? It is actually complete, right? If you have a metric space that is complete for, norm space that is complete for a norm, and that norm is actually equivalent to another one, then that metric space is also complete for an equivalent norm, to keep it short. So A and O with the new scalar product is a Hilbert space, and using, I think it was theorem 5.5, because I don't want to write again the Rees-Richet representation theorem. So using the Rees-Richet representation theorem, we may now represent phi, right, which was the end of the dual space, right, through the new scalar product. Right, so this means that there exists a unique, call it G, right, in H, such that this dual pairing phi comma v is equal to the scalar product. The new scalar product will be A of G comma v, and of course for every v in H. Now observe that problem 10, right, that we proved already. Observe that problem 10. I can recall problem 10. That was actually find u such that A of u comma v minus u is actually greater or equal than phi, the dual pairing of phi and v comma u. So observe that problem 10 actually amounts to finding some u in K, right, such that A of G minus u comma v minus u is less or equal than 0. Right, I just I brought the left hand side to the right hand side and also use the identification that we made, right, of the dual pairing of phi and v to be A of G comma v, so and use the linearity of A. So problem 10 among to this, right? So let's call this second reduction 16, right? Now the solution of 16 is the solution of 16, it's an old friend. Oops. It's an old friend, right? You should think of it a bit deeply. This is an old friend. U is simply the projection onto K of G, right, for the new scalar product. It's an old friend, so this is U is the projection onto K of G, right, for, we just put it here, U is the projection onto K of G, right, for the new scalar product. So if you haven't watched the video on the projection, on Hilbert space, some elementary properties, I strongly invite you to do so, because in that video I actually went through the projection theorem and explained all this basic fact. Okay, so U is actually the projection onto K of G, right? So you may, you also know that this is just a consequence of, again, the projection theorem, right, that I was talking about. This was theorem 5.2. Please check it out. So you also know about the projection theorem that U, right, is the unique element in K, right, such that the norm of G minus U, the norm U, right, which we define to be A of G minus U, comma G minus U to the power 1 over 2. You also know that this is actually, this minimizes the distance of G to K, right? So this is the mean over the V in K of A of G, minus U, comma G minus U to the power, V here, to the power 1 over 2, right? So this is again another way of saying that U means the argmin, right? This is not an abuse of notation. Argmin, of course, should be a singleton, but U is the argmin of A of G minus V to the power 1 over 2, right? So this is exactly equal to the argmin over the V in K, right? Of the function squared of A of G minus V, G minus V, right? Now what you can do is actually observe that we use the bilinearity of A to see that this is A of V comma V, right? Minus 2 times A of G comma V plus A of G comma G, right? But this quantity here this is independent of V, right? So this argmin is again the argmin of A of V comma V, right? Minus 2 times A of G comma V, right? Over the V in K, right? If you're not convinced, think of just draw a very quick picture for that. So think of this, for instance. So think of this, for instance, say this is 0, this is minus 1, this is 1, so this is the x-axis and the y-axis, right? And say you have, I don't know, you have a parabola, something like this. So you have a parabola, right? So, the mean of this function is actually attained at 0, right? So if you actually slide this, if you increase this in the, without changing the x value, the mean, the argmin doesn't change, right? But if I shift it up or down, the minimum stays at the same position, right? But if you change the position of this function in the x-axis, for instance, the argmin changes. So this is basically the main idea, right? So if you square this function, the argmin will not change, it will still be at 0. So this is basically why, the argmin of this is the same with this, right? Which is also the same with this. Okay, so I think this is clear. So so this means you have, use blue color. So this means U is the argmin of over the V in K, right? Of 1 over 2 of A of V comma V minus A of G comma V, right? But you should remember where the, with the help of the Reis-Fréchet representation theorem, and given also that A was actually, defines a new scalar product, you saw that this is exactly the dual pairing of phi and V, right? So finally we get that U is the argmin over the V in K of 1 over 2 of A of V comma V minus phi comma v, and this is exactly relation 11. So with this we end the proof of the Stampacchia's theorem. Okay, good. So now we can actually state its corollary. So this is corollary 5.8, I think so. This is Lax-Milgram. Okay, so now assume A define this Cartesian product into R, right? Is a continuous, cohesive, and bilinear form on H. Continuous, cohesive, and bilinear form on H. Then given any linear bounded operator phi in the Joule space, right? In H, element of the Joule space, there exists a unique, we call it U, in H, right, such that A of U comma V, right, is equal to this Joule pairing. And this is of course for every V in H. Right, so we call this second relation 17, right? And this is often called the, let's call it, this is often called L equation. Moreover, if A is symmetric, if our bilinear form is symmetric, right, then U is characterized by the following property. U is an element of K, of course, of H, sorry. Here we don't have any subset K anymore. So U is an element of H, and U is, is the argmin of the following functional 1/2 of A of V comma V minus phi comma V, right? This is basically the same result, right? Over the V, over the V in H. So let's call this 18. Maybe I put it in just to be consistent. Okay, so this was also supposed to be bound. Okay, good. So let's have a look at the proof. Okay, this is a, as I said, this is a consequence. 18 is 18. This one, right, is just, it's a consequence of Stampacchia. theorem, right, with k equals h, right? H is the Hilbert space, it is non-empty, convex and closed. So Stampacchia's theorem says that there exists a unique U in K, which is H in our case, such that I think 10 was actually A of U comma V minus U is greater or equal than phi of V minus U, right? And this is of course for every V in H. So this means, because H is a vector space, so this means this also holds A of U comma TV minus U, right, is greater or equal than phi of TV minus U, right, for every V in H and for every T in R. So this means for T strictly positive, right, you get that A of U comma V, right, minus phi of V is greater or equal than 1 over T of A of U comma U minus phi of U, right? So if you make T arbitrarily large, right, this actually goes to 0, as T goes to infinity, right? So this means that you get that A of U comma V is greater or equal than, just write it in terms of Joule pairing, right? Joule pairing of phi and V. Let's call it star 1. Okay, so for T strictly less than 0, right, the story is the same, and then we get A of U comma V is less or equal than, the inequality will change. So A of U comma V will be less or equal than, oops, I think we just write phi of V, right, those two, right, hence we have an equality. This is equal to this for every V in H, right? So yeah, that 18 is, as I said, 18 is immediate. So this is the end of the proof of the Lax-Milgram theorem, and probably also the end of this lecture. So thank you for joining me, and until then, stay safe, keep learning, keep striving for the best, and we see again each other in the next video. Bye.